Okay, so the way I like to think of it, the major ones for the law of sine are when you know two angles and a side. All right? Doesn't matter what order you put that in. You could say angle, angle, side, side, angle, 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 side, angle. Doesn't matter. We're looking for two angles and one side tells me to use the law of sines. So that list, law of sines, is going to include angle, side, angle, and then we also called it angle, angle, side, which is the same thing as side, angle, angle. Both those things are the exact same triangle. All right, that oddball case would be side, side, angle. And why I call it an oddball case is because if I put this on a test, if I put side, side, angle on a test, it'd be more or less determine how many triangles we have and solve those given triangles. Okay, so that oddball case. These two can just be in a bunch of triangles where I say solve the triangle and you have to know which one to use. All right, law of cosines. Well, that's going to be the other two cases where we have side, angle, side. And if we're given side, side, side. And remember, the good thing about these laws is it doesn't have to be a right triangle. Up until now, it always had to be a right triangle. These work for any triangle, including right triangles. Okay, yeah?
Wait, for the side angle, so wait, it wouldn't work if it was two triangles or something? Or
It wouldn't work if it was two triangles?
or was it just...
Well, it'd still work if it was two triangles. In fact, if this turned into two triangles, remember that one that we did in class? We had to use the law of sines twice for both triangles.
Oh, okay.
Because this could turn into actual two triangles. So you'd actually be solving for two triangles, even though it looks like I only gave you one. Not sure if you answered your question or not.
Yeah, that answer is it was oddball.
Oh, okay. Yeah, that's the oddball one. Because remember, this one had 4 different cases. It could be one triangle, no triangles. So why I say it's oddball is that you would already know it's side, side, angle, because I would have said determine the number of triangles first.
Okay.
Right? These could be all buried together. All 4 of these could be in the same category where I just says solve the triangle. And I have a whole bunch of triangles listed for you, a whole bunch of information. All right, this one should stand out to you because it's going to be a completely different section of the test. Or it'll be a new problem that says determine the number of triangles first, and then blah, blah, blah. Okay? Does that answer your question then?
Yeah.
Okay, good. All right, first thing, do we have any questions on the homework? Except for the fact that number 2 is actually number 3 in the book. Do you recognize that? I think I had auto numbering still on. I usually turn that off because it keeps trying to put things in order. I think I forgot on that one. It has been changed. Okay, a little easier of an assignment last night? Okay, this one should be a little easier too. Monday nights should be a little bit easier too. We're going to start talking about vectors. All right, we're going to start talking about vectors. And the only problem with vectors, they're not super complicated problems or in-depth where you have to think about a ton of stuff unless you get into physics. We're not going to get into physics problems. We're just going to do the basics on vectors. It's just a whole bunch of information I'm going to kind of throw at you. So it's just going to take a little bit of practice and knowing the given formulas. Based upon that, I do want to tell you that for this test, this upcoming test, because it's kind of an oddball chapter, if anyone's looked through the different types, it goes all over across the board. I might let you use, and you're going to have to remind me when we get closer to the test, I might let you use just a note card where you can put whatever information you want on that note card. Okay? Just to make things a little... Nothing, because I already know it all. Okay, so we're going to get into vectors. A vector is just a line segment that has both direction and magnitude. Magnitude is just length. So we have over a certain distance. Now, vectors are usually used for, and you probably saw it a lot in physics, they're used for like force. They're used for directional force, speed force, that kind of thing. They're typically used for different types of force. And what they look like is they almost look like a ray. The only difference between a ray and a vector is that a vector starts and it stops. So this one let's list that as A. We'll call that B. So a vector has a starting point and an end point. That's how it has magnitude. It has a specific length. It doesn't actually go any further than this. Even though there's an arrow, it stops right here. It doesn't go any further than this. Whereas a ray technically goes on forever. All right, that's the only difference between a ray and a vector. So we have magnitude and we got direction. We're going to put some information on here. First of all, we're going to put our notation. How do I first write an N, apparently? Notation. Little notation. How are we going to say that this is a vector without having to draw a vector every single time? So the first way we can do it is we can just do an A, B, and we put a line on top, kind of like when I'm drawing a vector on top. All right. Unfortunately, this is the exact same notation you use for array, so you have to know the connotation whether it's array or whether it's a vector. So that's one way to note it. The other way is more for if you're typing something because it's boldface. You're going to use a boldface letter. So if I was using V, I would use a boldface V, so it's bold. And that could be a lowercase or an uppercase letter. So this vector we could either call AB or we could call it boldface V, boldface B, boldface C. Do you have a question?
Yeah, just this is dumb. But what defers this vector from like a normal line segment? Like since it has two dots.
What delineates it between it?
Yeah.
So a line segment, you don't know what direction you're actually traveling. This is the actual direction this vector is going. We'll have like vector fields that you can see like a direction. So if the wind is blowing, it's blowing this direction versus the regular segment, you wouldn't know which way the wind is blowing. And it's really important because if you notice, and based upon John's statement, I wrote this as AB. That means A is the starting value and it's going in the direction of B. So if I would have written B first, that would have been wrong because that would have been the wrong direction. This is our start point. This is our end point. Start point, end point, important when you write down what your given vector is. All right, let's also talk about magnitude real quick. Magnitude is just going to be the length. What is the length of that vector? So this vector here would be different than a vector way up here. This vector would be longer. All right, its force would be greater, as opposed to one that was like shorter, that would have less force, but it'd be a different vector. Each vector has a specific length. And how we write magnitude is we just use absolute value signs over our regular notation. For instance, if I see this symbol here where I have absolute value around that AB, that means what's the magnitude of that vector that's inside the absolute value. Same goes for if I use boldface, we just put absolute values around that. And I'll be honest, a lot of times these boldface turn into regular. It's just hard to write bold. It's easier to do this, but the book uses a lot of this notation, and it's hard to switch between the two. So you'll see yourself just having a lot of just regular V's. And as long as you know you're talking about a vector, it's not going to be a problem. Note the absolute value signs. They let me know that magnitude needs to be positive. Needs to be or it can be 0. But I assume we know that something can be 0. So anytime I read magnitude, I should think I'm going to get a positive answer out of this. All right, so that's the long and short of what vectors are. And I'm glad John asked that question because I think I'm going to bring that up from now on when I delineate between, because it's an important distinction between the two. All right, the next thing we're going to talk about is scalar multiplication. Scalar multiplication. All this is going to do is it's going to change the magnitude of my vector. And we have two tugboats here. We have two tugboats. We got a yellow one and a red one. Yours is like a gray and then a different gray, I guess you might say. All right, so we got a lower one. And this line, this vector that's right by this tugboat is symbolizing its force that it's applying to this barge. If you look at the tugboat above, it has a longer vector. That means it's applying more force to that barge. So it probably means either its engines are bigger or it's just more revved up. And if we look at this A, my vector is called A here. This is twice A. So what that tells me is if that tugboat on the bottom, if that thing is pushing or pulling that barge at 2,000 pounds, if that's how much force it's exerting on it, then the top tugboat is actually exerting 4,000 pounds. And we get all of that from either just this number or drawing a vector twice as long. So that's how important vectors can be, especially to, who remembers that from when you took, why am I drawing the blank of the class? I said it before. Physics, thank you. Who remembers vectors from physics? Or did we just blank that from our memory? Like physics, I didn't even take it. Yeah. But you spend a lot of times with vectors just because it's really easy to use vectors and that drawing to show very complex matters. Okay, so that's what's called scalar multiplication. I'm going the exact same direction. I'm applying the force to the exact same item, except I'm either applying more or less. So how that might look in drawing, we're going to start out with a vector. Just a regular vector. Ugh, that's too long. And I'm going to call that vector A, B. So as soon as I put that A, B on there, I can call this vector A, B. All right, that's my vector A, B. If I'm going to apply more force, I'd multiply by a number bigger than 1. So let's say we have a scalar multiplication of 2. Well, if I just want to draw that, it's just going to be this exact same vector, except it's going to be twice as long. It's just going to be twice as long, so bless you. So this vector is going to look more like this. Same exact direction. It's just a little longer. Well, it's twice as long. A scalar multiplication can even take down the amount of force or the length of our vector. So if I want to do like 1/2, if I do half of that same starting off vector, it's going to look just like AB. It's just going to be shorter. So it's just going to be, let's see, that kind of looks half. Now the weird thing, gentlemen, the weird thing about scalar multiplication is if I put a negative in front of it, this distance is going to be the exact same because I did not scale it. I did not change the scale on it, so the size is going to be the exact same. Let's see if we can do it almost exactly the same. We're still going to have B up here. We're still going to have A down here. The only difference is it changes the direction my arrow goes. All right, so if I'm a tugboat and I'm going this direction, I'm pulling in, that's A. Negative A would be I'm pushing it the opposite direction. The exact same direction, just I'm facing the other way. Okay, so that also tells me that if I ever have negative vector, it actually equals the vector BA. So negative AB actually equals the vector BA. Because remember, when I list it, when I'm naming these, it's the start to the end. So my new start is B, my new end is A. All right, and that's scalar multiplication. That is what scalar multiplication is. All right, when I use vector addition or subtraction, let me get stuff signed, loaded up here. Just give me a second. So I want that to be a line. Let's do that. Let's do spacing like that. Okay. So when I'm adding two vectors, so let's say I have vector A that'll be the bottom one, and vector B will be the one on the left. Those are my two vectors, A and B. I use boldface so I can just use one letter, and that's okay. Let's say I want to do A plus B. All I have to do to add two vectors, so where this might come in handy is maybe we're back at the two tugboats, but the barge has one chain attached to it, right? And we have one tugboat pulling this direction, one tugboat pulling this direction, because you can't put them next to each other because they'll be banging against each other, so they're kind of pulling in different directions. But I want to see how much force combined they're applying to it. That's when you would add. That's when we add vectors together to see what happens when I combine those two forces. Because when I combine this force to this force, you don't just add together. If this was 2,000 and this was 1,000, it wouldn't be 3,000 because they're pulling in slightly different directions. So when we add these together, all we're going to do is I'm going to say, I want to know what tugboat A plus tugboat B is going to be. So I want to do A plus B. All you're going to do is you're going to run to the end of A, and you're going to literally add B onto it. So you're going to take this section and basically move it over here. I'm going to do that with a dashed red line. So I'm going to add B to it, and all I'm going to do is I'm going to run, let's do it in blue, I'm going to run a new vector going right up to that point I just created. And this would be A plus B. Although my next one's going to come up with the exact same answer, notationally they are different. This time I want to know what B plus A is going to be. If I'm doing B plus A, it's going to be the same, right? Because it's 2 plus 3 or 3 plus 2. It's going to be the exact same. However, I'm going to run up B, and I'm going to add A to it. So visually it looks different, but at the end of the day we're going to come up with the same solution. So A or B plus A is going to be when I run that way. So I attach A to it, and so the upper one is going to be B. Let's use the big one, B plus A. Not the biggest deal breaker in the world when you're adding, but when you subtract, it's going to make a big difference which one you start with and which one you finish with. So we're going to do subtraction on this guy. And what I'm going to do is I'm going to label them the exact same. I'm going to call the bottom one A. Let's call the one on the left B. And I want to do B minus A. So when I added A, it made sense because I had a positive A, so it's going to go in the same direction. But if I'm subtracting A, that's a negative version of A, so it's going to go in the opposite direction. So rather than adding it this way, I'm going to add it the opposite direction. So for B minus A, I'm going to run like this. And I'm going to draw a new vector in that direction. So this is basically our negative A. That is our negative A distance. Should have made it a little bit longer. And so this would be B minus A. I don't really have room on here to do it, but if we did A minus B, that would be run out to A, and instead of going this direction, I would go this direction with B, so I'd end up down here. In fact, this would make a straight line, but you'll notice they'd be two different vectors. So be careful if you're subtracting, because it really matters which one you do first. This method of drawing vectors is called tip to tail. Tip to tail, because you take the tip of one and you start with the tail of the other one and you go to tip. Alright, so drawing vectors is pretty easy to add. On Monday we'll talk about how we add them together mathematically. So if I just give you a couple numbers without drawing it, can you add them together? Okay. Horizontal and vertical components. Just like when you have a point on a graph, it has an x value and it has a y value. The same thing is going to happen with vectors. However, we call them horizontal component and vertical component. How far did it move horizontally? How far did it move vertically? Christmas is white enough for me. All right. So think of it as just like the xy plane. And in fact, it basically is the exact same thing. And if we look here, our horizontal component are our x values. Our vertical component are our y values. That's why we call it w sub x, w sub y, to let you know that we're using the xy plane. Everything is the same. So don't make this more complicated than it is. It's the xy plane. This is x values, these are y values. All right, if I want to find, if we're looking at this drawing, I did not note yet, but just so you know, that r that's sitting there, that r right there, that's going to be our magnitude, okay? R equals our magnitude. So that's some positive number that tells me this length. That's some positive number that tells me the length. So we're going to let r be our magnitude. That's that length of the line. Well, if we look at what I created here, I created a right triangle where we have a specific angle. All right, we have a specific angle there. Angle, right triangle, my x value, my x length, well, that's adjacent. This is hypotenuse. We must be using some kind of trig identity there, or trig function. And in fact, we are. We're going to use cosine. So we're going to use cosine of that theta to relate our horizontal component with our magnitude. And that's going to be adjacent over hypotenuse, so that's just going to be our horizontal component, which is w sub x, all over our magnitude, which is r. And if I want to solve for wx, we're just going to multiply both sides by r, and we're going to come up with w sub x actually equals r times the cosine of theta. I want to stick with the same triangle because I would have known this degree measure. I don't want to figure out this degree measure and relate it to y. So I want to use this exact same angle. However, this is on the other triangle, but we note that this distance here is the exact same distance here. So I'm just going to move my wy and I'm going to put it over there so we can see that our vertical distance is actually the same thing as this. So I just move my vertical distance over there. Now I can relate it to this same exact angle, except now we got opposite over hypotenuse. So we're going to have sine of theta is going to equal our opposite, which is our vertical, which is w sub y, all over our magnitude, which is r, which tells me that if I ever want to find my vertical component, or my y value, I'm just going to take r and multiply it by the sine of that theta. All right, let's go ahead and use this. We're going to find the magnitude. I'm going to stop right there and I'm going to circle magnitude, because magnitude means that it needs to be positive. Whatever my answer is, it needs to be positive. Of the horizontal and vertical components for the vector v with magnitude 8.3 and the directional angle 121.3. In fact, everything in there gives me all the information I need to just plug and chug, but I'm going to draw a drawing first. So we have magnitude, that was our r. We have an angle, that's our angle. We're done if we just recognize that. So we're going to go ahead and draw a picture of it though, so we can see what vector they're talking about. So I'm going to go ahead and draw an xy plane. I'm going to figure out where 120 degrees is. Well, 121.3 degrees, that's bigger than 90, less than 180, so we'll put it right there. That is my 121.3 degrees. So my vector is here. And we know the length of that vector. That length of that vector is going to be 8.3 because that's its magnitude. We're looking for what distance does it travel this way, and what distance does it travel this way. And distance is positive, that's why magnitude is positive, all we have to do is plug in the information. Well, if I'm looking for my horizontal, well, that's my Wx, my W sub x. And so using that formula above, W sub x, or my horizontal component, is just going to equal my magnitude, which is 8.3, times the cosine of whatever angle I'm given, and that's 121.3 degrees. Now, I know it has to be positive, so I'm going to take the absolute value of everything. And when I plug this into my calculator, I get out some number. Let me get my notes to the right section. Where are we? I'm going to get out negative 4.3. That means my magnitude of my horizontal component is 4.3. And note, I leave the absolute value bars on. Those absolute value bars tell me I am finding the magnitude. All right, this tells me the magnitude of my horizontal component is 4.3. All right, so those absolute value bars need to stay there when you're talking about magnitude. Okay, now we just got to find our vertical. Well, it's the same thing. We're going to do the absolute value of our vertical is going to equal our magnitude, 8.3, times sine of that 121.3 degrees. Don't forget that we're looking for the absolute value of it. So that means the magnitude of our vertical component is going to equal, I'm going to do everything, is going to equal 7.1. It equals 7.1. So once again, magnitude is absolute value bars around it. So if you see something with absolute value bars and it deals with vectors, we're talking about a magnitude. All right, that's why we leave those bars on the vertical and horizontal components. So if right now I went 4.3 units this direction and went straight up, I would hit that point. In fact, if I went over 4.3 and up 7.1, I'd be right here. That's where our horizontal and vertical, it's our x, y values. In short, it's our x, y values. All right, let's talk about component form. Well, I've been talking about x, y values this entire time, and our component form is basically just our x, y values of our terminal point. So the component form of a vector is a way to denote the vector based upon our horizontal and vertical component. This is achieved the same way we denote the horizontal and vertical components of a point on a graph. In other words, if I say the point 2, 3 to you, you would know where to plot that on an xy plane. Instead of using x and y values, because we're vectors, so we have to be different, we're going to use a. I'm going to say maybe this point is a out here. So I'm on the x-axis and I put an a at the very end of that. And I'm going to say this point right here is b. That would mean that the terminal point of that vector that's in blue up there is going to be the point a, b. The only difference from that point and what we're going to put for component form is those parentheses. Instead of parentheses, we're going to use slant brackets. So those little triangle brackets, we're going to do A, B, and that is now a vector and it's in component form. All right, as soon as I put those angle brackets on there in A, B, I know to put a point here and draw a line. That's what that tells me to do. That is component form, and that's it. Okay, we're done with component form. I'm also going to put, see how we have a vector down here? I'm going to put the component form of that vector. The component form of that vector would be a, comma 0, because it has no vertical component. Did that come up? Oh. There's more. All right, let me pause. Okay, So magnitude, notice that the vector creates a right triangle. So if I would drop a line down at AB, we would create a right triangle. And we're going to create a right triangle where we have a hypotenuse that has the length of the magnitude. We also have a vertical line that has the length of B. And we have a horizontal line that has the length of A. A squared plus B squared equals C squared. So to find my magnitude, our magnitude squared would equal A squared plus B squared. Well, then I would take the square root of both sides so I know what the magnitude equals. Where a magnitude will just equal the square root of A squared plus B squared. Okay, let's put everything we learned into this problem. We have to put a little bit of extra effort into this one. So it says find the magnitude and the direction angle of the vector -2, -5. So what I'm going to do is, well, I did it for you, but what I would do is I'd plot that point. I would draw a line so I know what vector they're talking about. So the directional angle is this guy. It's how far, just like a unit circle, how far counterclockwise does this vector go. In order to find that, well, I can't find this actual amount, but what I can do is I can create a right triangle. So with vectors, as we did with the unit circle, creating right triangles is going to be our way to get to a whole bunch of information. So that created a right triangle. We know that this length is -2, and we know that the vertical length is going to be -5, because those are our x, y values. So this length is -2, this length is -5. So that means I can find this little area right here, this little angle right here. All right, I'm going to call that angle, let's call it beta. All right, I have a right triangle, means I'm going to use a trig. I got opposite over adjacent, which means I'm going to use tangent. So we're going to use tangent to get to that. So we're going to say the tangent of our angle is going to equal opposite, which is -5, over adjacent, which is -2. I don't care what tangent equals. I want to know what b equals. So we're going to take tan inverse of both sides. And we're going to say our angle equals tan inverse of 5 over 2. And that means this angle is going to equal about, who knows, it's going to equal about 68.2 degrees. So this little guy right here equals 68.2 degrees. How much is this additional? How much is this worth? Or how many degrees is this? Kelly? 180. So the top one is 180. This little section is 68.2. So that means our directional angle is going to be 180 plus that 68.2, which is going to equal 248.2 degrees. That is my directional angle. All right, the only thing I have to do now is find the magnitude. Well, that's easy enough, because if I know my A and I know my B values, I can find my magnitude. Our magnitude, which we'll call magnitude V, is just going to equal our A squared plus our B squared. So that's -2 squared plus our -5 squared. So our magnitude is just going to equal the square root of 4 plus 25, which is 29. Magnitude's easy. Magnitude's easy. Oh, I forgot to put, let's just state that this is magnitude. That way when you're studying this, a couple weeks from now, you'll know which one was the magnitude and which one was your directional angle. All right, the very last problem we have, and we have enough time to do it, even though we had those technical difficulties, is find the component form of the vector of magnitude 40 miles per hour with directional angle 330 degrees. I'm looking for A, I'm looking for B. That's all they're asking for. I'm looking for A, I'm looking for B. To do that, all we're going to do is we're going to go back here. We're going to go back to these two equations where I have my horizontal and I have my vertical components. Note that your horizontal component is the length of here. So at the end of this is A. Our vertical component is how high it goes. That is our B value. So in fact, not only does this get us our horizontal and vertical, it also gets us our A and B values. So what I put on here is I just put, I wasn't going to go back to that slide, but we are anyway. I just put recall. Our horizontal component, that equals our magnitude times cosine of our angle. And our vertical component equals our magnitude times sine of our angle. But I just showed you that if I'm talking about my horizontal component, that is really just my A value. All right, but we're not talking about magnitude, so they can be negative. So I'm just looking for my A value. So instead of saying Wx equals that, I'm just going to say A equals R times cosine of theta, and B must equal that R times sine of theta as well. And that will get us our A and B values. So we just plug in our information. Well, that means A equals, our magnitude is 40 miles per hour, so that's 40, times the cosine of our angle is 330 degrees. Our B is just going to equal that same 40 miles per hour, so that's 40, times our sine of 330 degrees. That's going to give you, my A is going to be about 34.6. Let's not put degrees because it's not actually degrees. 34.6. And our B is actually going to equal a negative 20. Not magnitude, so we can have negative values, right? X, Y values have negative values. These have negative values. So that means the component form, this is how you finish off this problem, is 34.6, comma negative 20. This is component 4.